Hello, my name is Iago Menezes, along with academic Franciele Eiffel. We will present on project implementation and installation of light meter to use a Ldr sensor and microcontroller Arduino platform. We are students of Universidade Federal do Rio Grande, and this work is being present for discipline Controle e Automação de Processos Químicos 1, taught by Professor Dr. Renato Dutra Pereira Filho. Newton postulated the corpuscular mode of light, which described the light behaves like a particle. Years later, Thomas Young, Maxwell, Einstein, Max Planck, and some other scientists discovered that the light is a phenomenon of wave nature which propagates through materials and also propagated through the void. None of them was wrong. True is the light has wavy particle duality. Sometimes it behaves as particle, sometimes behaves as wave. In many situations, it's necessary to measure the light and the light intensity. NBR 5461 and 5413 are technical standards established by a consensus among researchers and professionals, and approved by ABNT, Association of Brazilian Technical Standards, regarding the definition of luminance and the type of appropriate luminance for each environment. Arduino is an open-source prototype platform based on easy-to-use hardware and software. Besides the physical part made up of microcontroller, the Arduino provides a development environment where the software is written, compiled, and sent to hardware. The Arduino boards are capable of reading entries such as the light in a sensor, process the information, and turn in the outlets, such as the activation of motor. Among the advantages of work with Arduino are low cost, helping forums for discussions and doubts, and others. The sensor LDR is an electronic component whose electrical resistance decreases, degrading the light energy incident on it, according to the equation, where the L is lightness and A and C are constants that depend on the material that the sensor is made. This photoresistor is made of light-resistant semiconductor such as cadmium sulfide and zinc sulfide. The greater the intensity of light energy inside in the semiconductor, more electrons have enough energy to jump into the conduction band. The free electrons conduct electricity, resulting in a lowering the resistance of LDR. The light meter is a device capable of measuring the intensity of light reaching the sensor. It can determine the quantity illuminance of a particular location.
The function of a filter is to remove unwanted parts of the signal, such as random noise, or extract useful signal parts, such as components with a particular frequency band. One of the most used types of filters is the exponential moving average filter, shown on the equation below, where Yn is the filter rate, alpha is the fit between past estimates and actual values between 0 and 1, and xn is the raw signal, and xn minus 1 is the raw signal of the old value. In this filter, weights are gradually growing in the entry of new observations, following the assumption that the most important observations are the latest to predict a new value in a near future. The objectives of this work are design, implement, and perform the settings of a low-cost light meter using an Ldr sensor and the microcontroller Arduino platform. Evaluate the calibration curve of the sensor according to the values measured in a commercial light meter, implementing an exponential moving average filter, and discuss the budget and the use of the alternative meter. The materials used are Arduino Nano 3.0, Atmel Atmega 328P, Mini Protoboard, Mini USB cable, Digital Multimeter PC Link VA18B, resistor of 330 ohms, Ldr sensor, digital lux meter CT1330B with accuracy of ±3%. The budget of the alternative meter was calculated based on values taken from the sales website Deal Extreme in June of 2016. The total value of the meter was calculated on R$30.99. The assembled metering consists of a voltage divider. The LDR was placed at the top of the divider according to the schemes showed. The LDR was connected to the ports 5 volts and A0, while the resistor was connected to the ports A0 and ground. On the implementation of the moving average filter, we used three values of alpha: alpha 1 equal to 0.1, alpha 2 equal to 0.2, and alpha 3 equal to 0.3. With alpha equal to 0.1, for example, the recent raw signal has a 10% weight, while the old signal has a 90% weight. On the calibration, three different light intensities were tested: dark lighting, light off, ambient lighting, light on, and lighting with flashlight, light on, plus lantern light. The values measured by the light meter lux were collected manually, while the input values provided by the LDR from 0 to 1024 were collected through the analog port A0 and automatically read through the Arduino. Both data were used to build the sensor calibration curve. On the calibration test, new brightness measurements were made for the ambient light range. The calibration equations obtained for each alpha in this brightness range were applied to new values measured by the LDR to test if the calculated illuminance would get close to the signal measured by the light meter. In this table, it is possible to see that the higher the brightness provided, higher the reading of the LDR and the reading of the commercial light meter. The LDR sensor operates coherently to be used to build the low-cost lux meter. The data provided by both LDR and the luximeter have a proportional relationship. Looking to this graph, it is possible to see the polynomial profile of the calibration curve. It was also analyzed the curves of calibration per brightness range for each alpha. Those are the curves for the dark lighting. Those are the curves for the ambient lighting with high coefficient of determination. And those are the curves for the lighting with flashlight. It is possible to conclude that only the measurements within the ambient light intensity range provided a reliable trend line. The lighting intensity is a very difficult variable to measure accurately. There are many noises that interfere with the measurement process, such as thermal, electrical, and random nature noises. Electrical noises are the considerable length of wire that captures more than the input signal, and also the Joule effect and the conductive materials used. The signal interference can be decreased by using shorter, thick, and insulated cables. As the thermal noise, we can talk about the temperature that increases the number of free electrons and the conductivity, decreasing the resistance of the LDR. Noises of this nature can be reduced by taking measurements in a controlled environment and preferably at low temperatures. Random nature noises come from variations in natural lighting environment and from the movement of persons on the measurement environment, causing shadows on the sensor.
The lux meter built is cheaper than commercial option of lux meter available on the market, being efficient to read the luminance in ambient light range to the use calibration curves. The filter with alpha 3 was the most effective in removing the noise inherent in the measurement. For other light intensity range, we're not obtaining good calibration curves. However, measurement in the closed room without the interference of natural ambient light and other carry could be alternative for obtaining a reliable calibration curves for various lighting tracks.